Today, let us discuss the principle of potential difference, or we call this as voltage. Now, in our previous video, we studied the electric potential, and we understand that for every point charge or point charges surrounding a point, surrounding in a point, we can always calculate the electric potential, and that potential is the rate of the energy per charge. So we come up with a unit of volts. Now today, let us use the principle of electric potential in order to produce a potential difference known as voltage. Okay, so let us recall first in the electric potential from a single charge particle. Now in our previous video, we understand that if we have the charge, positive charge, or it can be a negatively charged on a space wherein there is no other particle except its charge. This will, and it is in a stationary charge, this will produce charge distribution, and it forms electric field, just like Earth. The analogy is Earth provides the gravitational acceleration because of its mass. So in electricity, for every charge, it will generate an electric field, which means that it has the ability to interact with other charges because of its electric field. Okay, suppose if we have this moving charge Q naught in the region wherein there is a presence of electric field due to this stationary charge, then surely this particle will experience a force due to the amount of electric field at that point. So, what will be the electric potential? In the previous video, we understand that the electric potential of a single, by definition, of the electric potential is the electric potential V is equal to U over the charge unit. And the electric potential energy defined as the U equals the electric constant, or the 1 over 4 pi permittivity multiplied by the product of the two interacting charges divided by its distance between them. So therefore, these are the formulas to calculate for electric potential and the electric potential energy. Now, you are asked how much is the electric potential at the point wherein the charge is located. So therefore, the answer is we need only U. Okay? So it is U over charge. So substitute it here. Then we come up with 1 over 4 pi permittivity Q, the stationary charge, divided by the distance. Now take note that calculating the electric potential at this point does not require the moving charge. In other words, we can always bring any charge here, and you will be providing the same electric potential. But take note, if if we have the same electric potential for any charge placed on this point, but the energy varies, okay? Because energy requires the moving charge. The greater the moving charge, the greater the energy requires to move that particle. So therefore, this is the answer, calculating the electric potential. Now take note that because of that force or other factors that affects the particle to move, then there's a big possibility that this will be transferred from one point to another. Let's say this point start from here, then it ends up with this point. So the question is, what is the electric potential at that point at the radius RB, which is a distance that connects from the center of the point charge towards the point of interest? How much again is the electric potential? Nothing to worry, use the formula. This is 1 over 4 pi permittivity divided by the same charge, but this time we have a different value of the radius. So therefore, when you look at, if this is drawn to scale, then this will provide lesser amount of electric potential compared to this one. So these are the answers. If we are asked how much is the electric potential, it requires only, look at the formula, the charge and its distance. If you have the charge and its distance, you can always locate or calculate or provide the electric potential for different points away from the point charge. Okay, so therefore take note that we start at the initial position and we end up at the final position. So therefore, there must be a change in position or the displacement of the particle. Okay? So therefore, if we have the, why is it that this was displaced? Particle here and move it here. So the reason why is because of the force. And take note that there must be an electric force at this point. Because of the electric field present, there must be a force. If you want to calculate, then you can use the interacting charges using Coulomb's law, or you can solve it by multiplying the moving charge Q naught times the electric field at that point. Take note, different point in space in this field have different electric field. So therefore, we have this force. This is the force experience of the charge at this point. Then, once it was traveled from here going to this final position, then we have another force. Okay? So these are the reasons why the particle provides displacement. So therefore, we have the force and we have the displacement. So therefore, we have the work done. Okay? Because work can be done if there is a force, and that force was able to move the body. So suppose you are asked, how much is the work done of the particle moving from point A to point B? So you are asked to solve what is work done of this particle from A to B. What will be answered? Okay? To answer this question, we can use two formulas. In our previous videos on the electric energy, there are two ways to calculate the work done. Okay? We have calculating work done from A to B is you just take the change in electric potential energy A to B. So meaning you have to subtract the energy final minus initial because this is change and take the negative value because it is a negative change. So therefore, that's it. You can calculate the work done. So the requirement is you have to solve the energy 1, energy A and energy B. Then another formula is the general formula for the work done. This can be applied to any kind of force because this F is any force. It can be gravitational force, electric force, or any external or conservative forces. You can use it. It is you can just take the dot product of that infinitesimally because force might be changes. So if for varying force like spring or other uh, potential energies or potential forces, then you always use the infinitesimal value so that we can apply our integration process. So therefore, the work done from A to B is the integral of the that product of the force and its displacement, taking the limits from initial, this is the RA, and this must be the bar RB. So these are the two formulas. Okay. Now from the two formulas, we can provide two answers that have the same value. Okay. So first, we will use this principle. The work done from A to B is negative change in elastic or electric potential energy. So therefore, all you need to do is to replace the change by the final minus initial A to B. Then next is we can divide, if we divide both sides, okay, dividing both sides by the moving charge, so mathematically this will be, if you share denominator, this will be the answer. Okay. Now, why is it that we divide the moving charge? The reason is we want to replace U in terms of V, because take note, our our objective is to understand or to provide the potential difference. Okay, So, to provide a potential difference, the potential should be present on the mathematical equation. So therefore, we need to divide this one for the purpose that, look at this one. What is now, what is now U B over Q naught or UA over Q naught? Remember, this is the definition of what? Definition of electric potential. This is the electric potential. Okay? So the electric potential is U over the moving charge. So therefore, since this is UB, so therefore this must be what? UB over Q naught is the electric potential in the final point. This is the electric potential in the final point. Okay? While this one is the electric potential at the initial point. So meaning we can replace this U over B, UB over Q naught be equal to BB, while UA, which is the energy initial divided by the moving charge, replace this with U or BA, means the potential at point A. So therefore, this is it. Okay. So replacing this one with the in terms of potential. So look at this one. We call this as the potential difference. The VB minus VA, or the potential initial minus the potential potential final minus potential initial is actually a kind of potential difference. So therefore, this is already voltage, because the word potential difference is the same, or sometimes we can equate the two, because take note, the unit potential is volts, because joules per coulomb is volts. So therefore, if we have the two potentials, it must be the potential difference. We can provide a potential difference, and the potential difference is voltage. So therefore, this is the result after using the formula. The work done definition is equal to the negative change in electric potential energy, and we provided the terms that contains potential difference. So leave this as, let us say, equation 1. Now take note, if we remove the grouping symbol, then we come up with the potential initial minus potential final. Okay, so let this be equal to, let us say this is equation 1, and we will still have waiting for the result of another way to calculate the work done from A to B. So this time we will use this one. Okay, so what will you do? Now all you need to do is to replace the force. Okay, now take note, the dot product means you have to multiply the magnitude of the force and the magnitude of the displacement, and take the cosine of the angle between them. Okay, the angle between the infinitesimal displacement with force is the angle P. Okay, now take note that the force at any point of travel is the product of the moving charge and the electric field at that point specifically, which means that if the particle is at this point, force is the electric field multiplied at that point multiplied by the moving charge at any point. So therefore, we can replace this one. Okay, at, take note, this is a varying force. This is will keep on changing. Okay, now we can replace this in the presence of Q naught multiplied by electric field. This Q naught will not change. So the only variable that changes is the electric field. So the electric field, take note, is keep on changing while the particle travels from point A to point B. Okay, so therefore, again, if we divide both sides by Q naught, this one. So therefore, take note, this is constant, so we can move this outside from the integral sign, because integrating a constant is remain constant. So take it out, then divide it both sides by Q naught, then this will be the result, which means that the Q naught will be cancelled in the right term, or left term, or right member of the equation. So therefore, leaving this kind of equation. Okay, so therefore, take note that we are forming work done from A to B divided by Q naught. And take note, in our equation 1, we have the work done from A to B. So these are the same. Okay, so which means if we equate this to, or we say it equation 2, we can equate 1 and 2. So if you equate 1 and 2, why? We can equate because this is the same and this one. So equating 1 and 2, what will be the result? The result is the potential difference BA minus BB is equivalent to the integral of E cosine B, ranging from the initial position towards the final position. Now, how important is this formula? How important is this formula? Okay. This formula, take note that the voltage can be computed by, if you evaluate the integral involving electric field and the angle between the displacement. So therefore, with this, you can solve for the potential difference or the voltage in terms of the electric field. So therefore, take note that we studied on how to provide electric field on different charges, no? In a point charge, in continuous charges, we calculate the electric field. So therefore, we will use it today. We will utilize the principle, substitute in the electric field, then integrate, and you are providing the potential difference. Okay. Another important of this problem is, uh, okay, this is the potential difference. Another important is, we can always find the electric potential at any point of the point charge, or any charges. Why? Because this is the electric potential initial and this is the electric potential final. So meaning, if we want to know how much the potential at that point, we can use this formula. Okay, and we will relate the electric field. So therefore, aside from the voltage, we can solve the potential difference because this is a potential initial, this is potential final. So if you want to know how much is the potential initial, then you have to find the potential final, and you have to evaluate this one so that you can solve for the initial, or you can solve for the final. Okay. Now, the best thing to do with this formula is, take note that if we are asked to solve for the potential initial, then you can place this anywhere you want the final position. Now, take note that in a far away distance from the charge, the potential is zero. Okay. So when if you place this in the infinite position, the final position be placed in the infinite position, or maybe the initial position you place it in the final position, in the infinite solution, then you can, one of these can be equated to zero. In that process, you are calculating the potential at any point of the charge distribution. Okay, so this is a very, very important formula. Because why? This involves three quantities. We need the quantities. For example, again, you can calculate the electric potential of 2 points, or at any point. Okay, so then you can also calculate the voltage, and you can also calculate electric field if you want to. Okay, so therefore, this is a formula that involves many quantities: the electric field, the electric potential, the potential difference, and you can also solve for the energy. Because take note that potential is related to the energy. Okay, so okay, now take note that the meaning of cosine, and this is the magnitude of the vectors, we can use the dot product. Okay, so the general form of this formula is the potential difference from A to B is equivalent to the integral of the E dot dr, dot product. Okay, so take note that the meaning of potential A to B is the potential difference from A to B, from high potential to a low potential. So meaning you can say it from high to low. So if this is very low, this will be zero, because in the low potential, say it zero. Okay. When can the potential become zero? If this point B is located in a far away distance, infinite distance from the charge. Okay, so that's it. Another is we are always using the battery, no? And the battery has the voltage depending on the what kind of battery. For a dry cell battery, we have the 1.5 volts. Okay, so what is the meaning of 1.5 volts? In the car battery, we have the 12 volts. Why is it that it is a 12 volts? Okay. In a battery, if you have the 1.5 volts, meaning it is a potential difference. It is the difference in potential from A to B, from high to low. Now in this case, this is the positive terminal will be our point A, and this is a high potential, and this is a very low potential. That's why the negative terminals we call that as ground. Sometimes we call it as a ground. So if it's a ground, it is a zero volts. Okay, zero potential, and we have high potential. So therefore, in the high potential A, this is 1.5 volts, and this is zero. Take the potential difference. The answer is zero. Okay, so take note that if we place a charge here, the charge will move downward. Okay, so therefore, by just like a gravity, it will move downward until it reaches to the ground, and the ground has the energy of zero. Okay, so these are the important things to study about the potential difference. So therefore, if you want to have a greater voltage, take a greater difference, because the difference between the two potentials is the voltage. So therefore, if we have only one potential, you cannot provide voltage. The requirement of having voltage, we should have two potential. Then you have to take the potential difference. The result is voltage. Okay, so therefore, that's the principle of the electric potential difference, or we call it as voltage. Okay. Now, sometimes we hear the word electron volt. Okay, if you heard electron volt, it is a unit. It is a unit. This is another unit of electric potential energy. Take note that the word energy, in SI, the unit must be joule. Okay, but there are cases, or most in our actual application of energy, electric energy, we use the electron volt equivalent. What is the meaning of electron volt? Okay. Now remember that the electric potential is U over Z, or the energy divided by the moving charge. Okay. Now if we take the diagonal product, the energy now becomes Q times the potential, which means the Q has a unit of coulomb, and this is the unit of volts. Okay, and this is the unit of joule. So the unit of U is joule, this is coulomb, and this is volt. Okay, so from there we can say that 1 joule is, it's 1 joule. This is coulomb volt, and we understand that joule is what? Newton meter. Okay, so coulomb volt. By the way, so therefore, what is the meaning of 1 volt? 1 volt is 1 joule per coulomb, dividing both sides by volt. Okay, so a coulomb, dividing both sides by coulomb, this will becomes volt. So 1 volt is 1 joule per coulomb. This is the meaning of volt. Volt is joule per coulomb. Okay. Now look, going back to this definition. Again, how can be an electron volt formed? Okay. Now, if we have one electron as a moving charge, when you consider a one electron traveling, then place that on a region where the electric potential is 1 volt. Okay, so if this is 1 volt potential, and this is single electron, one electron, that's the meaning of electron volt. Okay? So therefore, the unit of this energy is an electron volt. So the question is, what is the relationship between the electron volt and the joule? How much joule for every electron volt, or how much electron volt for every joule? So we need the relationship. Now the relationship two is taken from this definition. Okay, so if we replace we understand that one electron is 1.602. Okay, multiplied by 10 raised to negative 19. This is one electron. Okay, then this multiplied by 1 volt. So what will happen is 1.6. But look, what is volt? What is volt? Volt is what? Joule per coulomb. Okay? Joule per coulomb. So therefore, replace this with joule per coulomb. This coulomb will be cancelled out. So what is left is the joule unit. So therefore, the 1 electron volt is equivalent to what? 1.602 times 10 raised to negative 19 joule. Okay? This is very important. Which means that for every electron volt, there are 1.602 times 10 raised to negative 19 joule. Easy to remember because we understand that the charge of one electron is, the charge of one electron is 1.602 times 10 raised to negative 19. And the unit is coulomb. Now, if you multiply this 1 volt, this will become joule. So that's electron volt. Okay? So, that's it. Okay, let's have the application of this formula derived. Remember this formula we derived previous slide? The electric potential difference in terms of electric field. Okay. So consider a parallel plates. Okay. Now we understand that in the parallel plates, the electric field inside are constant. It means it doesn't depend on the position. At any point, at any point in the region, this region, the electric field is the same. Outside, it varies. Okay. Now we understand also. Okay, but if there is space at a distance d. Okay. Now take note that in our previous videos in Gauss law, application of Gauss law, we or previous topics, okay, electric field is defined as the surface charge density over Q naught. This is for the parallel plates. For single plate, if you have only one plate, this is surface charge density over 2 permittivity. Okay, so if you wish to calculate how much is the electric field inside, okay, because this is inside, the answer is what? Electric field is equal to the surface charge density over the permittivity. So therefore, it does not depend on the distance. Okay, the same electric field for a parallel plates. For a parallel plates, this should be going to infinite, or the distances are very very small, in such that d becomes negligible. Okay, so this is a parallel plates. Now our task is to what? To calculate the potential difference. Okay, how much potential difference produce in terms of electric field, which means that the potential difference is, take note, the difference between the potential from A to B. So if this A to B, okay, now the best thing to do is to overlay the Cartesian. Why? Because we can set the Cartesian at 0 at the line of the negative charge plate. Okay, so therefore, the charge at any point here will travel. So therefore, in that case, we have the potential A as at the point, and we have the potential B. And this is a high potential, and this is a low potential. So meaning, if you imagine a charge Q naught there at this point, this Q naught will travel downward. Okay, just like a gravity. If you place a stone above the table, then release, the stone will move downward. Why? Because of the gravitational acceleration. This one also, if you release this one freely, this charge will move downward. Why? Because the force pushes the particle down. Because in the positive, it is outward, while in the negative, you will be attracted. So therefore, the lowest potential is at the origin. If this is zero, then it follows that we have the zero potential in the final. Okay? For a non-zero, then say it a low potential. When you say low potential, low volts. Okay, the lowest voltage volts. Okay, the potential difference is voltage. Okay, because voltage is quantity, volts is a unit, so we cannot equate the two. So meaning, if we release this charge, this will move downward, move downward. Okay, so if it is moving from A to B, it is because of the potential at A and the potential at B. Okay, this is the result. The potential at A and B. So the question is, how much is the potential difference from A to B? So look, we use this formula. Okay, this is the application of this formula. So all you need to do is, okay, take note that if you are looking for the potential A to B, okay, so therefore this is high and this is low because we set this as the origin. So therefore this can be equated to zero. Okay. Now what is the integral of electric field? Our task is to solve for the electric field or the potential difference in terms of electric field. Okay, so all you need to do is integrate. Okay, the limit should be what? It should be from zero because from initial. What is your initial? A. This is initial point. So therefore, R should be D. Okay, then the final is zero. So this is the because your particles reference is at the origin. So therefore, this must be initial must be the initial must be your D because the particles start from A. So this must be D, and the final is zero. Okay. Now take note that this one angle between the displacement and the electric field is zero. So therefore, cosine zero becomes one. Okay. So what? How much? Oh no, no, not one. Okay, because you are traveling from A to B, and this is our reference. So the angle must be not zero. It is 180. It can be a negative 180 or it can be a positive 180. Straight angle. Okay, because your positive y is upward and your electric field is downward. So therefore, it is an opposing due to our orientation of our Cartesian. So therefore, the angle must be 180. And that we understand that cosine 180 is negative 1. Okay? So replace the value, take it outside from the integral. The cosine of 180 is a constant, it is a negative. Then we have the electric field. At that point is also constant. Okay? Then we have only the integral from d to 0 of the infinitesimal displacement. So therefore, the integral of dr is, take note, is r. Okay. Then take the limit. Okay. Take the limit from d to 0 or from ra to rb. So evaluate the limit. Take note, this is negative because cosine of 180 is negative. Then this one is apply the limit. Okay. So it should be final minus initial. This will provide negative 0 minus d. So therefore, negative negative becomes positive. So therefore, what is the potential difference from A to B? It is just the product of the electric field times the distance between plates. The distance between plates multiplied by electric field is the potential difference from A to B. Okay? So, if you have the value of the surface charge density, because whatever the charge at positive will be the same charge and negative for a dipole principle. So then, equate this, then we can provide theoretically the potential difference. Notice the application of parallel plates. Now, in our coming videos, we will discuss the capacitor. So this is very important because the typical application of parallel plates is capacitor. So in the capacitor, we are required to solve for the voltage between the plates, parallel plates. So it should be the potential difference. So in this case, for a parallel plates, you just multiply the electric field and the distance. Okay, this is very important application. So we can say that the potential difference from A to B is just the product of the electric field times D. This is only for what? For parallel plates. Okay, so therefore, if you wish to calculate how much, if you know the potential difference, then divide it by D, the answer is still the electric field. Okay, look at the result. Now, what will be the unit of this? What will be the unit of electric field if we use this formula? This is, what's the unit of potential? This is volt, and this is meter. So therefore, we have another unit of electric field. We can use this one. We understand, using the formula, this is volt, okay? Volt per meter. So volt per meter is the unit of electric field. In other words, the 1 volt per meter is equivalent to 1 Newton per coulomb. So therefore, you can use this unit as volt per meter, or you can use the Newton per coulomb because they are equal. This is SI. Okay, this is SI. Now let's apply the problem again. We have the formal problem with numbers. Suppose we have a charge, and the charge is 3.5 nanocoulomb, and it's distributed over the surface of the metal, meaning the surface was occupied with a positively charge of 3.5, and the radius of that charge particle is 24 centimeters. Okay, 24 centimeters. This is 20 approximately. This is the radius. You only have the times because radius is 1/2 diameter, so therefore, more or less, this is the charge. Imagine, in a charge, there must a charge over the entire surface. Take note, the charge stays at the surface only. There is no charge inside. That's why the electric field inside is 0. Okay, but the electric potential is the same as the surface. Okay, so if the electric potential is 0 at the infinite point of infinity, which means that from that point of interest to, or from that source to the infinite, the electric potential is 0. Okay, because when you use the formula, if you are looking at distance of infinite, r is going to infinite, so you have to divide a very big number. So approximately the potential at that point is 0. So this is okay. This we can use this one because take note, we have this formula. Potential difference requires two potential, so we will utilize the uh, point at infinity. At infinity, the potential is 0, so we can assign that as B later on. So, okay, find the value of the potential at the following distances from the center of the sphere. What is the electric potential at 48 centimeters? That's from the center of the circle. Okay, then calculate again the electric potential at 24. So take note that 24 is the radius. So therefore, in letter B, you're asked to find how much is the electric potential at the surface. Okay, then at the 48 is outside the sphere. So this is outside. This is at the surface. The 12 is inside. So what will be the electric potential of A, B, and C problem? So to answer is, you have to construct the charge picture of the charge. This is approximately, or this is our charge, large object. with charge of 3.5 nanocoulomb outside. Okay. So then, okay, then we need 2 points because we will be using this one. Okay, we will use point A and we will use point B so that we have the RA, okay, and we have RB. Take note, RB, we can place this at infinite distance away from the point charge. Okay, because take note, we have here at the potential is 0 at point of infinity. So therefore, this will be our potential B. So we have now the potential difference. Okay, so RA is our initial, or RB is our final. In the final, it has a low potential, so it is 0, approximately 0. Okay, so let's derive how to calculate the potential at what? At the point. How much potential at point A? Take note is 0. And we will utilize this formula. Okay. Now, take note in our previous topic, if you are asked to calculate the potential, what are the requirements? The requirements are the charge and the distance. So meaning, if you have, we know already how much is the charge. The charge is 3.5. Divide it by R, okay? In our question, this is 48. Divide by R, then multiply it by 1 over 4 pi permittivity. That's it. That's the answer, okay? But this time, we will solve this one in terms of the potential difference formula, okay? So, this one. We can use this if we have the potential difference. In this case, we are guided that 1 point is 0 at infinity. So therefore, if this is our point of interest, this will be our point A, and this will be our point B final. So using this formula, okay. So now let's evaluate. Okay, take note this is cosine. Okay, so replace with the cosine, the angle. And take note, this is what? This is 0 angle P. Because the angle of the electric field is outward and the position is the same direction. So therefore, this must be 0. The cosine of 0 is 1. So meaning we can eliminate this one. And the electric field varies. Okay. So, okay. What is the electric field at that point? In our previous topic, calculate electric field is, it requires the charge and the distance only. So, 1 over 4 pi permittivity, okay, Q over R. This is the electric field. Okay? This is the electric field at that point A. Or maybe at point B, or at any point. This is representing at any value of R. Because we are talking about point A and point B. So, therefore, okay. So then, take note that R varies. So therefore, this is not a constant. But this one is constant, this is constant, this is constant one. So we take it out, okay? Then what we have now is, inside the integral, we have only 1 over R because everything was put outside. Q must be outside. So Q over 4 pi permittivity, the integral of 1 over R dr. So then, the integral of this is, take note, we can put it in the numerator, but then the exponent becomes negative. Okay? Then we can apply the basic rule, the power rule. This should be added by 1. Sorry. We have a wrong formula. This must be, okay, this must be r squared. Okay? Kindly correct. Pen. Okay, na pen. This is r squared. This is r squared. Okay. Q. Please correct. Can you correct this one? The electric field definition is Q over r squared multiplied by constant. So therefore, this must be square. Okay, this is square. This is a typographical error. Okay, this is square. Okay. Then the integral, you have to add this plus 1. Okay, integration plus 1. This will becomes negative 1. Okay, so therefore, take note this is 0. Okay, so therefore, what we have is this is what plus 1 becomes minus. Okay, so negative, this will using the power rule. Then divide it by n is negative 2 plus 1, so negative. So therefore, this is negative. And the negative 1 will, in the numerator, move under the denominator becomes positive, exponent 1. So therefore, this is the integral of the r raised to negative 2 dr. Okay, so kindly correct, this is 2. Okay. Now, okay, so take note, this is from RA, okay, this is our RA now. From RA going to the infinite result. These are the limits, no, from RA to the infinite. Then this one is 0, okay? So we can place 0, then apply the limit, upper minus lower, okay? So 1 over infinite, this is a large number, so this term becomes, approaches 0. And this is negative, negative becomes positive. So therefore, if you are calculating the potential at point A, because the question is what is the potential, okay? So the potential at point A is equal to 1 over 4 pi permittivity Q over R. Remember this result? This is the result of what? The definition of electric potential. So therefore, we we are just using the formula, okay? But this, where did we get this result? This is coming from the potential difference term, okay? So therefore, now replace A with letter A, 48. So therefore, this is 38. So from the formula, replace with, this is constant, divide by R, okay? Then the answer is 65, which means that the potential at this point is 65.63 joules. Okay, letter B, your R, where's your R? From the center towards the, because this is 24 and the radius is 24, so therefore, it must be at the surface. Okay, then replace that, the same, except R, then calculate 131.25. Look at the result. Our A is at 48 is 65.63. Our R of 12 at the surface is 131. So this provides the largest potential, because the largest potential is at the surface. In letter C, you are asked to solve for what? The electric potential inside, and that will be 12 centimeter. This is 24. So the 12 centimeter, okay, centimeters is approximately, or at the center. So what radius divided by 2? What is the electric potential at that point? What is your answer? Okay? Now take note that the maximum potential is at the surface. Okay? Moving away from this point, far away, approaches 0. But inside is constant, the same. The R is 12. It is inside the sphere. Inside the sphere, the potential have the same value. So therefore, the answer is equal to 131.25 automatically. But if the question is what is the electric field this inside, the answer is 0. Why? Because there is no enclosed charge. Because electric field is related to the flux. If there is no charge, there is no flux. If there is no flux, there is no field. Okay? So therefore, these are the answers to the questions. These are the answers to the question of calculating the. Take note, we are just using the formula before. But we use to solve this problem using the relations. Okay? Now there are many problems to solve in order to exercise this concept. Okay? So all you need to do is to try this. Try this. If you want to verify the concept we discussed today, try to solve this one. Okay? So uh, that's all. Okay? Our topic next video, we will calculate the electric potential of continuous, what will be the electric potential at the ring charge, okay, line charge, and so on for continuous charges. Question is it the same formula to be used? Let's see in the next video. Thank you.